Welcome back. So we saw the last time when we talked how we hinted at how large disturbances, right, in pressure and density can conceivably result in phenomena that are qualitatively different from what we encounter with small differences. In particular, we hinted at the possibility of discontinuities forming. And today we will have the occasion to talk a little more about these discontinuities, which are called shocks. Okay, but before starting to talk about large disturbances, before plunging into large disturbances and shocks and things like that, I thought I would touch a little bit upon one issue with regard to small disturbances, with regard to sound compressibility, with regard to the relation between compressibility and the Mach number. This is something that you will hear occasionally now and then as you go along in fluid dynamics, and I also mentioned this in the passing, but I thought we would take a little bit of a detailed look at this. So just to emphasize, for the next 5 or 10 minutes, we are not yet talking about large disturbances. We are now examining the relation between compressibility and Mach number. In particular, to understand why it is that subsonic flows are generally regarded to be incompressible, whereas supersonic flows are regarded to be compressible. Actually, the more accurate statement would be the effects of compressibility are crucial to examining to understanding supersonic flows, and conversely, the converse statement is applicable for subsonic flows. But there are some subtleties here, and I thought we would examine these subtleties a little bit before we go forward, right? So what is it? Right. So like we said, we remarked that incompressibility approximation is generally a good one for, in particular, very subsonic flows. In other words, the more subsonic the flow, the better the incompressibility approximation. Right. We've said this, and you'll also encounter this statement here and there. So let's try to understand why and how. Right. For simplicity, let's restrict ourselves to steady state situations. Steady state simply means this statement, right? In other words, the time variations as discerned by an Eulerian observer, an observer who's outside the flow, who's standing in the lab frame and watching the flow go by. For that kind of an observer, there are no time variations. Okay, just for simplicity. So in the steady state, we know that the mass conservation equation is just this. Why is that? Because in this, in the Eulerian frame, the mass conservation is simply, right? This is the mass conservation equation, and so if this first part is 0, we are left just with the second part, and so this is what I mean here, right? Now, we know, we've repeatedly emphasized this, that the incompressibility condition is this. This is the incompressibility condition. So what does that translate to here? You just apply the product rule for differentiation, right? So suppose in one dimension would be something like rho du dx plus u d rho dx. You agree with me? Right? So this is just the product rule, right? So never mind the dx's, right? So this is the kind of logic which leads to this statement. So if this is much less than 0, or rather if this is approximately equal to 0, right? And we know that this is almost equal to 0, isn't it? This is essentially this in one dimension. So if this is 0, in which case this had better be 0, which means that u del rho is much smaller than rho del u. In other words, this is much smaller than this. So this is the main thing. This is the main statement that we need to focus on, and let's keep this in mind. U del rho is much smaller than rho del u. This follows from the steady state mass conservation equation. Alternatively, you just divide by rho here. You have del rho by rho is much smaller than del u by u. So this is the other way of stating this, very important condition. And now Let us now write the steady state momentum equation. Again, just to remind you, the steady state simply means, this simply means, right, partial d partial t is equal to 0. So, the steady state momentum equation now it can be written as this, the Euler equation, neglect viscosity, right, and using the same logic this can essentially be written as u del u, and this can be written as 1 over rho del p, and we relate the del p to del rho using the sound speed, right. So, instead of del p we can write del rho here, del rho divided by cs squared, and using this you can do a little bit of rearrangement to write del rho over rho is equal to u squared over cs squared del u over u. Now, if you remember what we wrote in the previous thing, we said del rho over rho is much smaller than del u over u. That is what we got from the mass conservation equation, right. So, right, that is what we got, and compare it with this. If this is to be true while this is also true, there is only one way it can be true, right. The incompressibility condition, this, so this and this together imply that, strictly speaking, the Mach number squared is much less than 1, because that is what this is. There is the Mach number squared, right. Well, if the Mach number squared is much less than 1, it also means that the Mach number is also much less than 1, and vice versa. So, this is the basic thing, right. So, in other words, and where did this come from? This came from the fact that this was predicated, this comes from i.e. incompressibility. You remember that, right? In other words, incompressibility implies that the Mach number is much less than 1, and vice versa. If the Mach number is not much less than 1, in other words, if the flows are somewhat supersonic, then the incompressibility approximation is not so good. So, we now find that the same medium can be compressible. So, see, here is the other thing. There is no such thing as incompressible or compressible. It depends. Is a medium largely incompressible or is a medium largely compressible? It depends. It depends upon whether the wave speeds are sub or supersonic. Okay. If the wave speeds are subsonic, right, then incompressibility is a good approximation, whereas if the wave speed which you are talking about are supersonic, then incompressibility is not such a good approximation. So, this is one of the main things I wanted to emphasize. However, having said this, there is a conundrum, right. You might wonder about this. If the flow speed is subsonic, well then, you know, the medium can effectively be thought of as incompressible, but I thought you know, the air in this room is essentially still. There is no velocity at all, isn't it? So, you know, the wave speeds are definitely subsonic, essentially 0, and yet you are talking and sound waves are reaching me, and I thought sound waves were an essential, I mean, no compressibility, no sound waves, right. Sound waves and compressibility go hand in hand, isn't it? So, they are reaching me. So, what gives? What's up? The key here is that the wave speeds are sub or supersonic in the lab frame. As we said earlier, always the perturbations, the small perturbations that arise out of my speech or my clapping my hand or something, these small perturbations always travel at the sound speed, exactly the sound speed, and they travel at the sound speed with respect to the background flow, if any. So, to the Eulerian observer, okay, what will happen if there is a background flow, then the sound speed gets added to the background flow, whether it's in the plus x direction or the minus x direction or anything. Okay, and it's that added speed which should be either subsonic or supersonic. So the speed is with respect to the Eulerian observer. Whereas when you are in the frame of the flow, small perturbations always travel at the sound speed, exactly the sound speed. There is no question of whether these small perturbations are subsonic or supersonic. They are exactly sonic. So, this is something to keep in mind. So, this entire statement, okay, is true for the lab observer. Okay. So, when you hear this statement often that subsonic flows essentially incompressible, supersonic flows not so incompressible, yes, all that is true, but this is to do with the lab observer, not with a Lagrangian observer. Okay. So, and for the Lagrangian observer, sound waves, i.e. small amplitude pressure and density disturbances, travel at exactly the sound speed. They are sonic, they are neither subsonic nor supersonic, they are bound to be sonic, there is no other way around it. Okay. So, I thought I would re-emphasize the small aspect with regard to the speed at which small disturbances travel. They always travel at the sound speed with respect to the background flow. Okay. So, this is something that you need to keep firmly in mind before we go on and start talking about large disturbances, where this whole thing about linearization and everything breaks down, and it's with regard to large disturbances that we will examine the interesting phenomenon of shocks. So, we will do that in just a second. Thank you. So, having talked about having clarified a little bit about the relationship between Mach number and the sonic or supersonic nature of the background flow, rather the relationship between the Mach number, which tells you something about the sonic or supersonic nature of the background flow, the relationship between that and compressibility or incompressibility, having talked a little bit about that, and all this is about small disturbances, of course. Let us now get back to starting to think about the following question. What if the disturbances aren't small? In other words, what if the waves are not weak? Okay. In other words, what if the linearization assumption doesn't hold? This is what I mean by this statement. Okay. In other words, i.e. products of quantities with subscript 1, right, say rho 1 and say u1, right, never mind this, right, rho 1 and say this is a 1. Okay, I beg your pardon for this, cannot be neglected. So, if the waves are not weak, in other words, if the disturbances u1 and rho 1, u1 and things like this are large, then the products of quantities like rho 1 and u1 cannot be neglected anymore. Okay. So, instead of the linearized mass and momentum equations, we now have to consider the full equations, right. And for simplicity, let us restrict ourselves to one dimension. Okay. So, you have the mass continuity equation in 1D, right, and this is momentum. Okay. You can verify this. So, you have these two, and what we are now going to do is this the familiar jugglery. So, these two equations you add and subtract. Okay. You add them first, that corresponds to the plus sign here, and you subtract them, and that corresponds to the minus sign here. Okay. And so, you add the equations and you get du dt plus 1 over rho cs dp dt plus u plus cs, and here also the plus sign is to be considered equals 0. And you subtract them, and this entire thing with the minus sign here, here and here, that is valid. That is what this means. Okay. And I strongly urge you to work it out. Okay. And you realize where we are going with this. We are trying to figure out something like a Riemann invariant. You remember the J plus and J minus that we talked about when we met last. So, but those J pluses and J minuses were for the linearized mass and momentum equations also in 1D. Here there is no linearization, because we are considering a condition where the perturbations are no longer weak. Okay. So, you have this, and this can be cast, again I urge you to show this in the following useful form like this. This equation, this entire thing can be written as this, where the quantity f is nothing but dp over rho cs, which is 2 over gamma minus 1. Again, I urge you to carry out the algebra, which So, what you can see now is it's really this quantity that's advected along. This is again an advection equation, because this is a d over dt of this quantity plus u plus cs d over dx of the same quantity is equal to 0. So, if you consider just the plus signs all along, this means this represents a situation where the quantity u plus f, where f is defined by this, is propagated unchanged. In other words, is advected, okay, with a velocity u plus cs. Similarly, the minus sign of the equation represents a situation where the quantity u minus f, where f is again given by this, is advected without change at a velocity u minus cs. That is what this means. Okay. So, in other words, we have a conserved quantity that propagates forward or backward, okay, along the characteristics with a speed v plus or v minus cs. So, if you are talking about the forward characteristics, it corresponds to v plus cs. If you are talking about the backward characteristic, you are talking about a velocity v minus cs. So, you can already see the wave can be either supersonic, in other words, it can be v plus cs, or it can be subsonic, v minus cs. And v itself can be anything literally. And I urge you to examine how this equation is different. This is an advection equation, just like the advection equation we wrote down for j plus and j minus, and the other two Riemann invariants some time ago. And I urge you to compare these two equations and note the difference. What are the similarities and differences? The similarities, of course, is that both of them are advection equations. Both of them talk about conserved quantities, but the conserved quantities themselves are quite different. Okay, so I urge you to think about them. Now, what happens here? With the weak waves, what you could have is the forward and the backward characteristics. The forward characteristic which propagates at v plus cs, and the backward characteristic which propagates at v minus cs, they can intersect to give you a unique solution. So, that can happen here too, as with the weak waves that we talked about earlier. That can happen now too, right? Okay, but in this case, since you remember this thing that we discussed a little earlier, consider a pressure pulse, and the P is here, and let's not talk about for simplicity, let's not bother about density variations. Let's only bother about pressure variations for the time being. And if the pressure pulse is large enough so that the sound speed here is larger than the sound speed here. This is the leading edge and this is the peak of the pulse. Okay, but since the sound speed here can be larger than the sound speed here, there is a possibility that this can overtake this as time goes along. This feature propagates faster than this feature, and there is a possibility that this feature can overtake this feature, and there can be a wave breaking of sorts, right. So, that is what I mean by this. So, two forward characteristics can intersect, not forward and reverse characteristics. Two forward characteristics can intersect, indicating that the solution, and this is in some sense, this leads to non-unique solutions. This thing, okay. If two forward characteristics can intersect, it leads to non-unique solutions. I urge you to think about this. And what that means is that the solution can be double valued, okay, which is to say that there can be, it hints at the presence of a discontinuity or a shock. And I will put up an article by Lax, and this they give a little more of a general discussion. So we will do that, and I will put that up, and I'm only giving you sort of the essence of that discussion, and there's a lot more to be said about this very interesting thing, the fact that for the situation where the disturbances are not small, you can have intersecting characteristics, but not forward and backward characteristics intersecting, but two forward characteristics intersecting, and that leads to this mathematical problem. okay, of non-unique solutions, and that essentially leads to the realization that such solutions can contain discontinuities, which we will realize, and some of these discontinuities can be what are called shocks. So we will talk a little more about shocks in the next segment, and but this issue about characteristics is dealt with quite extensively in this article by Lax, which I urge you to read. So we will stop here for the time being. Thank you.